Hello and welcome. In this video we're going to look at the Introduction to Probability. Module 4 is not necessarily something that will be tested heavily on the midterm or final. In fact, there are two different homework assignments for Module 4. One homework assignment is assigned, and the second homework assignment is optional extra credit because probability is important for us to understand for statistics in order for us to make statistical applications where we try to predict future outcomes of samples. But we don't need to necessarily know all the ins and outs of probability. So the first portion of this lesson, the first video that you're watching right now, will be what is like really important for us to know and understand, and then the second video will be kind of optional for those of you that are struggling with probability. It's completely doable, and I suggest that everyone watch the second video and try the second homework as the extra credit optional assignment on Lumen. But for this first video, let's just focus on the important stuff within probability. So an experiment is the planned operation carried out under controlled conditions. We're going to be looking at a bunch of different experiments, and basically that's where we are defining what we're doing within the example or within the problem. An outcome of an experiment is any result when performing the experiment. So we could be looking for green, or we could be looking for the number 3, or we could look for those that failed a test or something like that. So that would be the outcome. An event is a particular set of results or set of outcomes of an experiment. Probability is a numerical measure of the likelihood of an event occurring in the future. For experiments such as flipping a coin, rolling a 6-sided die, spinning a 4-colored spinner, and so on, you can find the probability of an event occurring with the ratio or fraction probability of event E, often written as P of E, similar to function notation for any of you that have taken an algebra class, which is equal to the number of ways that the event E can occur divided by the total number of possible outcomes for the experiment. The probability of an event can only be a number from 0 to 1 inclusive, or in terms of percent, from 0 to 100% inclusive. So our probabilities will always be between 0 and 1. They can never be negative. They can never be beyond 1. And then we have a few examples here. It says the probability of rolling a 4 on a 6-sided die. Well, this one's pretty straightforward. A 6-sided die has 6 outcomes, so the total number of possible outcomes is 6. Only one of them is a 4, so the probability would be 1 out of 6. The probability of rolling an odd number would be 1, 3, or 5. So there are 3 options out of 6, which is equal to 1/2. The probability of getting a heads on a coin flip would be 1 out of 2. There are 2 options for a coin flip, either heads or tails. One of them is heads. And the probability of spinning a green on a 4-colored spinner, this would be 1 out of 4. Now we're going to get into what's called the complement of an event. The complement is spelled with an E. This is the probability of an event not occurring. So the probability of not event E is often written as P of tilde E, or P of not E. I've also seen it as P of E with a C as an exponent. The probability of not E, or the complement of event E, would be the total number of possible outcomes minus the number of ways that the event E can occur, divided by the total number of possible outcomes. Another way we could look at this is we can find the, I should have also included this. We can also write this as the probability of E prime, or E with an apostrophe. The probability of the complement of E is 1 minus the probability of E does occur. And I'll show you this with an example. In example 4.1, it says the probability of rolling a 4 on a 6-sided die is 1 out of 6. So the probability of not rolling a 4 on a 6-sided die would be whatever's left over. So we can use this formula here, which would be 1 minus the probability of getting a 4, 1 out of 6. And what's left over? Well, there are 5 different options, or 5 different possible outcomes. The probability of rolling an odd in the above example was 3 out of 6, so the probability of rolling not an odd number, or not rolling an odd number, would be 1 minus 3 out of 6, which would be the remaining 3 out of 6, or of course 1/2. The probability of not getting a heads on a coin flip would be 1 out of 2, because it'd be 1 minus the probability of getting a heads on a coin flip. And then the probability of not spinning a green on a 4-colored spinner, well, if there is one green, then the probability of not getting a green would be whatever else there is. In this case, it'd be 3 out of 4. We need to get into a little bit more definitions here. It says 2 events, A and B, are independent if the knowledge that one occurred does not affect the chance the other occurs. We'll see some examples in a little bit. I'm just going to leave it as the definition for right now. Basically, the probability of one outcome does not affect the probability of the other outcome. And a sample space is a representation of all the possible outcomes of an experiment, and it can be found by making a tree diagram. And then we have an example here. It says, assuming the likelihood of a cat having male or female kittens is equal, a little typo there, sorry about that. Assuming that the likelihood of a cat having male or female kittens is equal or the same, find the sample space for this cat having 2 kittens or 3 kittens. So the sample space is, again, a representation of all the possible outcomes of an experiment. So for the 2 kittens one, it should be pretty straightforward. We could have a male and a male, or a female and a female, or a male and a female, or a female and a male. There are only 4 possible outcomes. This is the sample space. We could make a tree diagram. Let me move this out of the way and I'll actually label this a little bit better. This is the sample space. We could make a tree diagram here. Every time, actually, let me do this. I'll write the cat here. Every time I draw a little line here, like I just did, that represents one outcome. So here's one level of outcome. The cat can have either a male or a female for the first kitten, and then we can use, again, a second set of lines here. This would be the second outcome. So if the cat has a male kitten for the first, she could have a female or a male for the second, and a female or a male for the second for either one, whether it's male first or female first. Again, this is the tree diagram. Now, the way that we can use the tree diagram is we look vertically. Here is the outcome of male-female. Here is the outcome of male-male. Here is the outcome for female-female. And here's the outcome for female-male. Now, the order does not matter for these. We're just looking at the total outcomes that could happen for this experiment. So I'm going to pause here for a second, and I'm going to ask that you pause the video and try to create the sample space and a tree diagram for the 3-kitten example. All right, so I'm going to start with the tree diagram here. Again, this is the mother cat. The mother cat has the first baby, the first kitten, or the first outcome of the experiment. Could either be female or male. If the cat has a female kitten first, there are only 2 options for the second. If the cat has a male kitten first, then there's still, again, only 2 options for the second. So again, each time that I draw these little lines, we're indicating the second outcome or the first outcome. Or now we can look at the third outcome. Which again, only 2 options, either female or male, female or male, female, or male, female, or male. Again, we read the tree diagram vertically. So this would be the option for female, female, female. And I'll expand on this and make this a little bit neater in a second. This would be female, female, male. This would be female, male, female, F, M, F. This would be F, M, M. And then this would be M, F, F, male, female, female. I'm running out of room here, so I will clean this up in a minute. I'm just showing you how to read this. Male, female, male. Then we have male, male, female, M, M, F, and then male, male, male. So again, this is the tree diagram. Next to it, let me just slide this over a little bit. Next to it, we could have the sample space. Again, the sample space is just where we list out all of the possible options. We could have female, female, oh, let me make this nice and neat. Female, female, female. We could have female, female, male. Female, male, female. Female, male, male. Notice that in the first two, I've kept the female, female for the first two outcomes, and then I changed the third outcome. For the second two, I kept it female, male, female, male, and then I changed the third outcome. That's kind of the easy way that you can build the sample space without having to draw a tree diagram every time. And then we can do the same thing. M, 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 F, M, F, M, M, F, F. And that would be all of the possible outcomes. You'll notice that there are 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes, or 8 possible pathways through this tree, and there are a total of 8 possible outcomes for 3 kittens. That'll come back up into play in the second video. Oh, I lied. I'm sorry. I thought I was going to end the video here, but I am going to do one more example, and actually I'm going to talk about these 8 possible outcomes right now in the fundamental counting principle. So the total number of outcomes can be found by using the fundamental counting principle. And when I was a student, this concept took me a really long time to fully understand. It's actually very straightforward and quite easy. I just overcomplicated it when I was a student. So I'm going to try and warn you not to do that yourselves. The fundamental counting principle is where we multiply the number of outcomes from each step of the experiment, or we could also just count the last row of a tree diagram. Now, some of our experiments are going to be kind of complicated, and trying to count a huge tree diagram is going to be a little bit difficult. So let's see how we could have used this for the previous example. So I generally like to show little lines here that show the number of outcomes for the first experiment, or the first outcome, or the number of possible outcomes, I should say. Let me move this down just a little bit. Have a little bit more room. Number of possible outcomes for the first kitten. Well, we could either have a male or a female, so there are 2 possible outcomes. Then we would have the number of possible outcomes for the second kitten. Again, male or female, only 2 outcomes. And then the number of possible outcomes for the third kitten. Again, only 2 outcomes, male or female. The fundamental counting principle says that we multiply the number of those outcomes. So 2 times 2 is 4, and 4 times 2 is 8. So that's how we can get the total number of outcomes using the fundamental counting principle. It doesn't tell us what those outcomes are, but just tells us how many we should have. All right, so let's look at example 4.4 And that will be the end of this video, and then you'll pick up on the second video with some more of the more difficult, a little bit more advanced probability topics, which again will not really be on any tests. They might be on a quiz or some homework questions, but I'm not really all that worried about these probabilities. I just want us to get a good understanding of what it means when I say probability for future statistics applications. So example 4.4 says, an experiment consists of a single roll of a die and a single toss of a coin. So maybe we're playing a board game, maybe we're, I don't know, doing something, and we roll a die and we toss a coin, and we look at the outcomes for those. Using the fundamental counting principle, determine the total number of possible outcomes. Well, the first thing we would do is roll a die. I'm assuming it's a 6-sided die, it doesn't say, so let's just go with 6. So there are 6 possible outcomes for rolling a die. The second part of the experiment says to toss a coin. Well, if we toss a coin, there are 2 possible outcomes, heads or tails. So that means that there are a total of 12 possible outcomes. Then part B says to construct the sample space. I'll construct the sample space. I'm going to use the same colors as I did before for B. I'll construct the sample space without making a tree diagram. But then right at the end of the video, I will make a tree diagram just to help anyone that's having a little hard time with this. So rolling a die. Well, if we roll a die, we could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. If we toss a coin, we could get a heads. So I'm going to put a heads with all of these outcomes. Or we could also get a 1 with a tails, or a 2 with a tails, or a 3 with a tails, or a 4 with a tails, or a 5 with a tails, or a 6 with a tails. And that is my 12 possible outcomes. If I wanted to make a tree diagram, I would have my first experiment, or first set of outcomes. However, when I did my first outcomes with the kitten example above, I only had 2 possible outcomes for them. Well, I actually have 6 different possible outcomes for this, right? It'd be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And then for each one of those, I have 2 more possible outcomes, which again would be the second set of outcomes. And each one of those would either be heads or tails, 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 heads or tails. And again, we can read this vertically. So this would be 1 with the heads. This one here would be 3 with the tails. 3 with the tails. This one here would be 6 with the heads. So that's where we would get the 12 different outcomes from for the tree diagram. All right, thanks for watching this video, and see you on the next one.